Today's webinar titled Enabling Functional Safety Automotive Camera Applications Using MIPI CSI-2 and MIPI Camera Service Extensions. During today's sessions, I'll be moderating, and again, I'm Peter Lefkin, Executive Director of MIPI Alliance. Haran Tenegasalam is a camera and imaging consultant for MIPI Alliance. Ariel Lasri is Director of Technical Standards with Qualcomm Technologies. He's a member of the MIPI Camera Working Group, among an active member of a number of other working groups as well, including AFI. The session agenda for today, I'll give a little bit of an introduction into MIPI and automotive. I'll then hand it over for the presentation on enabling automotive camera applications using MIPI CSI-2, and then we'll jump into the camera service extensions. So a very brief introduction to MIPI Alliance and automotive. MIPI Alliance has, we celebrated our 20th anniversary last year. We originally formed in 2003, right at the time when cameras and displays were being integrated into mobile phones. That was really our reason for being. And fast forward to today, we're pleased to be able to say that at least one MIPI specification is in every smartphone today. And we've developed over 50 specifications covering a full range of interface applications needed for mobile devices. The ecosystem has evolved over time, certainly over that same 20-year period that mobile has evolved. Primarily, we started with semiconductor companies, application processor developers, and IP and VIP providers, device OEMs, of course. So as the ecosystem evolved, as specifications were implemented in the marketplace, we rounded out the ecosystem with test equipment companies, test labs, additional IP and VIP provider came in, consumer electronics companies from all different application areas, and certainly automotive OEMs and tier one suppliers are an important part of the ecosystem and certainly an important part of the 2 days that we have here today. We have over 375 plus members, and over 50% of our members indicate that they are in the automotive sector. So one of our success factors has been specializing in high performance, low power, and low EMI connectivity. And certainly as mobile has influenced the ecosystem beyond mobile, we see automotive, we see IoT, we see medical, aviation, and a number of other consumer electronics devices as well. MIPI specifications are granted to members on a royalty-free basis for implementation, and that's for all MIPI members. The most recognized specs from MIPI in automotive in particular, CSI-2, DSI, RFFE, AFI, CFI, DFI, I3C, we're seeing more and more being considered and looked at for automotive as well. I don't expect you to see, but you can, I'm sure, pick out some names here with regard to the MIPI members in automotive. There's a number of OEMs that are listed there. There's some new OEMs, in particular one from the US that recently joined MIPI as well. I mentioned before the specifications in automotive. I won't repeat that, but this isn't aspirational for MIPI. MIPI has been in automotive for probably over 10 years now. Certainly camera, displays as well, and CFI, DFI in particular has been in automotive for a long period of time, and CFI we're seeing adoption as well. Moving forward, we see, and this is really just a framework that we've put together and a way of talking about the automotive SerDes solution for MIPI that cuts across the MIPI protocol layers, camera, LiDAR, radar, Camera Service Extensions, security and functional safety. We see protocol adaptation layers for CSI-2 and DSI-2 for AFI. Also, we collaborate actively with Visa for DisplayPort automotive extension. In particular, they're developing some security specifications as well for display, and EDP and DP can work over AFI as well. There's a number of other supporting interfaces: Ethernet, GPIO, MIPI I3C, I2C, SPI, and it's built to accommodate other protocols for the future. With that, I'd like to hand it over to Haran Tanagosalam. He's a camera and imaging consultant for MIPI Alliance, and he'll be talking about enabling automotive camera applications using MIPI CSI-2. Thanks, Haran.
Yeah, thank you, Peter. Good morning, everyone. When we think about the MIPI Camera Serial Interface, this is a high-level abstracted view of what an imaging conduit, CSI-2 imaging conduit is, spanning the application layer, protocol layers, and the physical layers. The CSI-2 frame format, it is comprised of packet header, which we often consider as a mission-critical content, comprising virtual channels to data types to error correction, error checking and correction, which is able to identify 2-bit errors and correct a single-bit error. What you see in magenta are the digital representations of the data that's coming from the pixel arrays, and that is coupled with a complementary cyclic redundancy checker. It's using a PRBS Galois 2 to the 16 polynomial, and there are a number of complementary specifications that within the umbrella of MIPI, Camera Workgroup works together in very strong, deep collaboration with 5 workgroups and software workgroups and I3C and conformance test suite to help develop a comprehensive imaging conduit solution spanning a myriad of product platforms. So that the 5 specifications include the DPHY, CPHY, APHY, coupled with I3C, and we do have the capability to transport pixels using I3C, which we'll touch on shortly. Conformance test suite to help de-risk interrupting the sensors with the application processors. The camera service extensions entail functional safety specifically for automotive applications, ISO 26262 requirements, along with end-to-end security. CCS stands for Camera Command Set as well as DISCO that come together to help develop baseline unified imaging software drivers. If we kind of zoom out the development spanning over 20 years, as Peter mentioned, there are 3 key pillars that stands as foundations for the CSI-2 imaging conduit solutions. One being an incredibly strong alignment between sensors and application processors. The second is that from an overall imaging conduit perspective, we bring multiple domain experts to help develop low energy transport. That includes the transmitter, the channel, as well as a receiver. And our ability to bring together around 400 member companies to better understand the applications that are just coming out of incubation phase that are standardization grade worthy have been incredible and of paramount importance. So as Peter mentioned earlier, this is an automotive system engineering problem that we were taking on about a dozen years ago. We have, in this case, a challenging light condition, and we have an automotive vehicle that is trying to identify the street signs. Here is a zoomed-in version of a 5-degree slanted edge. And the system engineering problem was the 5 transport network solutions are incredibly complex and costly. Could we explore a pathway to retain a means of transporting the CSI-2 frames without introducing compression artifacts. And that led to the development of the differential pulse code modulation as depicted here, specifically the 12-10-12 targeting number of automotive platforms. And the implication here is that we were able to reduce the burden on the PHY transport network by about 20%, while also reducing the maximum absolute error of a single bit change in pixel value by a factor of 4.43. The pathway of accomplishing this entailed going through various degrees of intensity, high, medium, low intensity qualifications, using the permutations with the low contrast, medium contrast, high contrast, and going through various modular transfer frequency response to track the original raw frame that is often used for machine vision applications. As Peter noted earlier, building on what we have developed for mobile platforms, MIPI CSI-2 has indeed continued to expand the scope for spanning applications within consumer imaging and vision systems, the commercial segment, as well as infrastructure. Just a couple of quick points. Within consumer segment, today at present, we see a number of MIPI member companies actively working towards developing native transport solutions for client products, specifically the next generation of video conferencing applications. For commercial applications, we do see considerable interest coming from member companies of supporting solutions for medical endoscopy applications and industrial surveillance. From infrastructure perspective, we do see robotics vision, real-time perception and decision-making, perhaps even using asynchronous event sensing and processing as some of the key developments that camera work group and PHY work groups within MIPI are presently working on. Power spectral density reduction is one of the key features or core features that we have for CSI-2 imaging conduits. What you see in the dark shade of blue on the left, it is mapped to the CSI-2 over D-PHY transport. Just by enabling PSD, we are able to bring down the emissions, which is incredibly important, particularly when you are placing the conduit near sensitive GPS receivers, for instance. Similarly, on the right, we have the same PSD reduction that could be equally used for the C-PHY transport, which has an embedded clock and data, where we see the dark shade of blue reducing the emissions. LRTE, latency reduction transport efficiency, is another core feature that is broadly deployed in the ecosystem. It's at core principle, what LRTE does is it removes the packet delimiters between the long packets that are typically mapped to horizontal rows of a sensor and replaces the packet delimiter with a PHY generated and consumed control code. And this has a number of benefits, including pathway for reducing overheads for sensor aggregation. This also has provisions included for alleviating dual voltage signaling. And the implication of this is that we are able to now natively support long reach without the need for bridges and retimers. This is a slide for offline review, where we have for a typical automotive self-parking application. There are, I believe, a dozen cameras deployed here. These are 2.3 megapixel, 12 bits per pixel, 60 FPS, global shutter type sensors. And just by enabling LRTE, we are able to reduce the overall network, PHY transport network burden by a factor of 23%, or conversely, using the existing PHY transport network, we could support 40% more sensors. Unified serial link is another important and an incredibly complex feature that MIPI Camera Work Group is undertaking. At present, the feature was developed and released as part of CSI-2 version 3.0, I believe. And at present, there are, coming from various imaging system model analysis, we have about 12 Bugzilla opens that MIPI Camera Work Group is is addressing and actively working on. Some of the key benefits of this feature includes wire reduction, which is a holy grail for any interface. And so here, the idea of encapsulating GPIO wires with the need for additional I2C, I3C SPI conduits for register access into a single half-duplex asymmetric bidirectional conduit is really what's at the core of the USL. It also has some advanced features like replay protection, particularly when we think about imaging systems, vision systems that are deploying smart sensors, which may require sophisticated firmware management. When we zoom out, we see broad adoption of the CSI-2 over D-PHY and CSI-2 over C-PHY sensors spanning multiple platforms. And here, this slide depicts some of the key differences. For the D-PHY sensors, we have the pixel data that is sampled at the rising edge and falling edge of the clock cycle. But these are all differential signaling. And for the C-PHY transport, we have 16 bits of pixel data that we are transporting over 7 symbols. And kudos to Raj Kumar, who's leading the D-PHY group, and George Wiley, who's leading the C-PHY group. They've architected the solution so that they are able to coexist. So combo C-PHY and D-PHY solutions are indeed possible, and we often see in the ecosystem such solutions existing. One of the another key present developments that MIPI Camera Work Group and the 5 work groups are working on is the embedded clock mode. This is a D-PHY embedded clock mode solution. There seems to be a lot of momentum and impetus in manifesting this feature. At a very high level, if you were to zoom out, in the salmon pink, let's say you have an application processor labeled as SoC-A, and that is using the traditional forwarded clock mode solution. And let's say this application requires 3 sensors, a by 4, by 2, by 1. Then when you are defining the roadmap and going through the development of this SoC, we will have to burn 20 high-speed I/O pins mapped to 3 sensors, a by 4, by 2, by 1, which in the development cycle, you would have to freeze them right at the pin definition level. Those are the orange lines. And so this has number of constraints. So let's say if for some reason we wanted to use this SoC-A for dual depth perception, maybe there is a product platform that requires depth perception as a portrait mode and landscape mode, then we will run into a number of issues because using FCM, we are limited to 3 camera sensors. Now, transitioning from the FCM, which is a salmon pink SoC-A, to the sort of a light green SoC-B solution, the one immediate benefit is that, let's say, even if we have the by 4, by 2, by 1 sensor requirements, that's going to result in pin savings of 6 high-speed I/O pins in this hypothetical example. So we do see pin savings as a key benefit of ECM, but more importantly, the prior constraint that MIPI D-PHY used to have for camera applications, which is ports are fixed at the pin level, it has been alleviated, or rather will be alleviated with ECM, mainly because the concept or the element of ECM enables the realization of dynamically configurable logical ports for camera sensors. Couple of architectures emerging from ECM. In this case, these are transitionary architectures where we can use the existing legacy camera sensors coupled with a translator module within a camera translator chip within a camera module to facilitate a 2-wire transport for product platforms that may be wire constrained or have narrow hinge openings. The difference between architecture A and B is that architecture A has a baseline camera sensor where all of the image processing is executed by the application processor. In architecture B, it is possible maybe the application processor does not have the ISP, and all of the ISP processing could be done within the camera module, or conversely, there could be a rudimentary ISP within the camera module that is working in a hybrid mode with the sophisticated ISP in the application processor. Architecture C and D are sort of the integrated versions of the prior architectures. Again, it goes back to one of the fundamental DNAs of the MIPI PHYs, and specifically the D-PHY ECM, is that it's being architected from ground up for it to be low energy consuming solution. So native integration becomes a possibility. And therefore, instead of having an additional translator chip, native integration into sensors are indeed possible with the ECM solution. One of the questions that often comes up with the ternary coding is the propagation of errors in links. And again, kudos to the camera work group and CSI work group. They have come up with this brilliant idea in which, should there be some kind of a Gaussian error when you're transporting pixel frames, it is resilient. So the worst possible location that a Gaussian error could manifest is going to be right at the end of the first packet header. And we have single lightning bolts, double lightning bolts, triple lightning bolts depicting the worst possible case conditions. And just by having that unique sync code as illustrated in the second last bullet, and coupled with the relaxing the way the sync code is detected on the application processor, CSI-2 CSI is indeed proven in the ecosystem to be resilient against various link errors. Similar to the ECM, the CSI-16B7S also has dynamic port capabilities on SoCs. It also has another unique feature, which is its ability to support beyond 16 virtual channels for product platforms that may require higher virtual channels. The 3-wire solution, which is a CSI solution similar to ECM, also has a transitionary pathway in which legacy sensors could be supported with the camera module. We often refer to this as a MIPI 3-wire solution, with and without the ISP integrated into the camera module. And as noted earlier, native integration is also possible with the MIPI 3-wire solution, again, transporting 16 bits over 7 symbols. The A-PHY has been developed specifically for automotive long-reach applications. And as the chairs and the leads working on the A-PHY have noted, this is an incredibly comprehensive SerDes solution that is emission resilient for a number of automotive worst case conditions and scenarios. It has asymmetric SerDes physical layer capability, but more importantly, it is also capable of supporting the mean time failure rate of just a single error over the entire lifespan of the vehicle. The solution is capable of supporting 15 meters using SDP, STQ, and coax cables. And the version 1.1.1 and the next gen 2.0 will also cover in session for tomorrow. The AOSC feature, it was developed to address a very interesting imaging system application, which is, can we support ultra low power consumption for perhaps monitoring a big little movement or something of interest that's running continuously. So that drove us to take a look at perhaps transport of QVGA type resolutions. Perhaps it's just a monochrome image that is transporting at, say, 3 to 10 frames per second, using the I3C that was developed on top of the I2C FM electrical signaling solutions. And so AOSC is a solution, it's an I3C based solution that we have for always on monitoring that does not require the MIPI C-PHY or D-PHY. Equally important, this solution has been defined in such a way that a sensor could operate in a hybrid mode. So perhaps when it's monitoring for that interesting event, such as, am I seeing a human face, it is using the I3C transport. And once it has detected that, then the same camera sensor could switch into a full resolution mode and then use the D-PHY or a C-PHY mechanism to transport the full frame images as well. So a lot of thought has gone into the AOSC feature, which is, again, one of the key features. This is for an offline review of the baseline operations of how the AOSC works for a broad range of imaging applications, from the on-demand frame control to initiate frame exposure to how we are transporting, how we are switching the I3C data rate, and then using a circular buffer type approach to transport or to read out all of the frame content from the sensor to the application processor. Smart region of interest was architected to reduce the bandwidth on a number of vision systems by selectively transmitting the rectangular regions of interest that may be of interest for that specific vision applications. Now, this again has two different flavors. There's the integrated smart region of interest where all of the inferencing, vision DSP processing are built into the sensor, perhaps using a multi-stack sensor solution. But it can also be deployed on vision systems using a rudimentary sensor coupled to a companion chip or perhaps the VDSP functionality existing within the application processor. Multi-pixel compression builds on top of the previously noted differential pulse code modulation. So the way I view this is that this is an evolved version of a compression solution that we have. Here we are using the statistical probability that a neighboring pixel is going to be similar, and it has some remarkable objective measurements, everything from a superior, around 14 dB peak SNR, PSNR ratio improvement, while at the same time compressing the data by a factor of 20%, more than what a traditional DPCM solution is able to compress. And the solution has already been adopted, and that is being used in the broader ecosystem. So in summary, MIPI CSI-2, we had the first mover advantage with the mobile phones, and we continue to leverage all of the learnings from the mobile phone for photography and video applications for a number of beyond mobile platforms, targeting both human consumption as well as machine consumption. The CSI-2 imaging conduit is used by a broad range and categories and classes of sensors targeting multiple platforms, evolved using D-PHY, FCM, ECM, C-PHY 16B, 7S, 32B, 9S, the A-PHY long reach transport for automotive as native integration as well as bridge solutions. We touched briefly on the core features and capabilities, including the raw frame CSI-2 transport, differential pulse code modulation, latency reduction to facilitate sensor aggregation, support long reach, scrambling to minimize PSD emissions, multi-pixel compression along with differential pulse code modulation, smart region of interest, unified serial link to reduce the number of wires, and always on sentinel conduit to reduce the overall system inferencing capabilities. This is typically for 24/7, 365 inferencing. We again welcome your feedback on expanding CSI-2 for beyond cameras, including radars, LiDARs, and sonars. We know they are being used in a number of automotive platforms. Your inputs will be helpful on if perhaps additional latency optimizations are needed. And we also have the camera interest group that's reporting into camera work group and working with the 5 work groups, where we bring both the adopters and contributors to help explore the emerging applications. So thank you. I'll take a pause, Peter.
Yeah, thanks, Aaron. So I'd like to introduce Ariel Lasry, Director of Technical Standards at Qualcomm, and he's a member of the MIPI Camera Working Group to talk about MIPI Camera Service Extensions enabling camera functional safety. Thanks, Ariel.
Yeah, thank you, Peter, for the introduction, and good day, everybody. I will introduce today only the functional safety part of the camera service extension. Rick Whitfield will introduce later the security part. So I will really focus on the functional safety. When looking for a camera in automotive, on sensor in automotive, it's important to consider end-to-end functional safety and end-to-end security protection. And why we are talking about end-to-end is because the component, for example, a sensor, camera sensor, and an ECU are not connected in proximity. They are not connected on the same platform. They are quite far from each other. Maybe you have a rear camera or side camera or front camera, and they are very far from the ECU. And for that purpose, often there are intermediate bridge to extend the reach of the camera, so to be able to drive, let's say, to the 10 or 15 meters. But you may have also in zonal architecture some zonal aggregator where you will have some forwarding element. So when starting considering the functional safety and security protection, we were thinking on the end-to-end protection using this 1 to 5 model reference topology, where we can have between the controller, which is the, let's say, the main ECU, and the sensor, we may have one bridge or two bridges, so one maybe only a serializer or a serializer and a serializer, and we may have forwarding element, like if we are in a zone. So all different type of topology have been considered to guarantee the end-to-end protection for functional safety and security. So, so this is a high-level diagram of the camera service extension. The camera service extension basically extend the CSI-2 protocol by adding a new data service protocol directly at the source of the pixel generation on the sensor and directly at the sink at the consumer ECU side. Yeah, and so this additional service protocol illustrated here in green and in blue. So first we have all the blue part, which is all the security. So we apply a security protection to the pixel data and the control data, and after that, this is going through functional safety protection. So if you want, it's the kind of encapsulation of security within functional safety. Yeah, and on the other direction, after it goes to the ECU, the operation is just reversed. And this camera service extension is completely agnostic to the physical layer because it comes directly above the CSI-2 layer. So we define the detection method of error for error detection, for functional safety, or for security, but how to manage the error, how to react on such kind of error, this is depending on the application, and this is out of scope of the CSE. So the CSE is really about how to enable error detection and how to detect that on application layer, end-to-end protocol. So looking at the functional safety, yeah, so we at MIPI, we follow the ISO 26262 standard, and more specifically, there is this Annex D of the -5 standard about communication bus safety mechanism. And there are a number of recommendations there. So for example, for information redundancy, we are using CRC32 with arming distance, which is greater than 3 for the detection of any communication failure. We are using a message-based counter and a frame-based counter. And here we denote a SEP or FSED, which are basically the protocol used for functional safety. And with SEP, we are rather using message-based protection, and in FSED, frame-based protection, although there are some capability for SEP to have also frame-based protection. I will come to that later. So information redundancy, which are message-based or frame-based. And then we have also frame counter. And again, depending if we are in a mode of frame-based or message-based, we have a message-based counter or frame-based counter. In addition to that, we have a lot of error testing, like built-in self-test pattern generation, so that it's possible to generate image data from the sensor in the test mode, and see on the receiver side that we get this specific beast image there with predefined image. And we are also able to inject error so that when integrating the design and checking is the system all operational and is the system able to detect functional safety error? Yeah, so this is why we inject error in the system to check, yeah, we are able to detect transmission error. There's also timeout monitoring, which is required by ISO, and CSE is taking care of that as well. And the one important thing is that we have a combination of all these mechanisms, and the combination of these mechanisms are there to be able for each design to claim high diagnostic coverage when making the functional safety assessment. So let's move on. So maybe some basic about a CSI-2 frame. Typically, this is how a single virtual channel of a CSI-2 is a single image frame is transported. So there's a frame start, synchronization signal, and then there might be one or more or zero or more embedded data packet shown in green here, which carry some sensor information. And after that, there are all these blue lines, which are the image data, which are the raw pixel data. And after this portion, there are the embedded data again. So embedded data can come either before the image data or after the image data in a CSI-2 frame. And there is a synchronization end packet at the end. And what we do is that we partition the frame for the purpose of applying various functional safety and security service. And we are able to apply different frame portion. So for different frame partition 1 to frame partition 5, different method for error detection on the link. So we are able to offer this capability, and I will show later. Now this slide is a bit busy, so this shows all the so-called CSE tag modes. Tag mode are basically the verification tags. So we have a tag is consisting of a MAC and CRC, for example. So MAC for security protection or message authentication code, and CRC for cyclic redundant check for functional safety. And there are different modes, and it is possible to apply for each frame partition different type of security protection there. And when I'm not going into the detail of the security tag mode, this will be explained later on. But for functional safety, we have basically two SEP functional safety tag mode. So these are SEP FUSA tag mode 1 and SEP FUSA tag mode 2. And in the SEP tag mode 1, we basically add for each packet its message counter and CRC. So as you can see in tag mode 1A and 1B and 1CD, yeah. And there's a SEP tag mode 2, which is a frame-based tag mode when using the SEP protocol. Okay. There's another protocol which is called FSED, like a frame-based service extension data. And the FSED is having only one only one functional safety tag mode. It has a multiple security tag mode. And this is always performed per frame. And what we do in FZ is we add additional packet, this orange packet that you can see on the right side, to transport the FZ information. So functional safety, we have either SEP or FZ. In SEP, we have two tag mode, message-based or frame-based for functional safety. And in FZ, for functional safety, we have only frame-based tag mode. So if I am now going more to the detail of the SEP protocol, so basically what we do is that we take the pixel from the sensor image data, and each line is carried over the long packet. A normal CSI-2 packet has a packet header and packet footer. And what we do with SEP is that we use a new packet header and packet footer, which are called SEP header and SEP footer, which take CSI-2 packet information like a virtual channel and data type and extend them. So we're able to extend the low number of virtual channels that we usually have in C5 or D5 to much more virtual channel in SEP. And we add also some redundancy information like a message counter. And in the SEP footer, we put the MAC message authentication code for security and the CRC there. And then this SEP packet goes over the long reach file, the A-file in this case, and then it is chunked because A-file takes only a shorter packet, so it's required to segment the packets to transport them. So for functional safety, we are using the message counter in the SEP header and the security counter in the SEP header for replay protection, the MAC in the SEP footer and the CRC in the SEP footer. And we are extending the packet header information of CSI-2. Yeah, that's what SEP is doing. When we are using the FZ protocol, so now the SEP that I've shown before is creating a new CSI-2 data type called SEP. Now what we're doing here with FZ is that we are using only so-called legacy CSI-2 packet, no SEP packet. Yeah, and with this legacy CSI-2 packet, what we do is that since we cannot transport the CRC and MAC within the existing packet, yeah, what we do is that we insert FZ messages in the beginning of the frame. Yeah, as we can see it after the frame start, we have a first message, FZ message, which is shown here in orange. And these FZ messages are carried as embedded data packet, like any normal embedded data, CSI-2 embedded data packet. We just specify the format of this embedded data in FZ. And so there is an initial control sync message, which set the parameter and frame information for the current frame for the further verification of this frame. Then after the top block, we may have a verification. So there's an optional FZ top tag message to check and verify whether the top block, the embedded data that were sent have been all sent without any error. So this is why we set the FZ top tag. It's a kind of header verification. And then at the end of the frame, we have the FZ frame tag that protect the full CSI-2 frame, and in which we have accumulated CRC and accumulated MAC that covers the full CSI-2 frame. Okay. So some word about the BEAST. So we have built-in self-test and diagnostics. So as I explained before, we specify 5 standard pattern for BEAST. These are specific image data that can be verified on the receiver side, just to check that the link is up and running. And it's possible to apply this test at any time during initialization, during runtime, or to apply them as many times as required. For example, every 1,000 frame, every 10,000 frame, whatever is specified. And it's possible to carry the image frame, the test frame, either embedded within the image frame, like on the left side diagram, or as a separate CSI-2 frame, like on the right side diagram. And in addition, yeah, as I mentioned before, we can add error to all these BEAST pattern. So to summarize what we are doing in the CSE for functional safety, so we are extending the well-proven CSI-2 protocol with additional function. We provide end-to-end functional safety and security protection directly at the application protocol level, completely agnostic from the file. And the end-to-end protection is provided to support various topology, including the long-reach file, aggregator, bridges, forwarding element, so that you can use them not only in the point-to-point connection, but also in complex automotive architecture with zonal ECU. And we also have support for both message-based and frame-based protection to enable system integration trade-off, whether we want to check every message or every frame. And we add support for self-testing and error rejection and various tag mode for claiming higher functional safety diagnostic level as per ISO 26262. Yeah, and that's it.
Great. Thanks, Ariel. Really appreciate it. And Haran, you can come back on stage as well. We'll jump into a Q&A session. And Ariel, since you're on stage, I'll start with you. It looks like there was a question. Will the CSI-2 link be teared down if BIST fails?
What we do is that we provide elements for detecting errors, okay? And then it's up to the application to decide how to act on each kind of error. And depending on the application may decide, yeah, I want to shut down the link, or I want to restart the link, or I want to do something else, yeah? Depending really on the application.
Great. Thank you, Ariel. I think this question is for you, Haran. Is there a method to connect the existing sensors to interface with ECM, kind of an adapter without the need to rewire?
All right, that's a very good question, Peter. So in our slide deck, I believe it's on page 22, we have an abstracted view of how a legacy sensor, like say a D5 FCM or a C5 16B7S, could be connected to ECM. And that said, this ECM development is presently in works within MIPI, Peter, like within the camera work group and the PHY work group. So again, highly encourage the member companies to participate in those discussions as we develop the solution.
Are all the CSE tag modes mandatory for implementation?
No. So this is where we provide flexibility for the design and the system integrator depending on the application. So you can use either FZ or you can use set, and you may use only one of the tag mode depending on the requirements of your application. So maybe, we'll take a very simple example. So if you are making it per message, you are going to have a very high overhead because on each message you are going to add CRC and MAC, and so depending if the application really requires that you verify every message, then for that application you will use that tag mode. On another hand, if the application is satisfied with verifying only once per frame, then you will use the tag mode that corresponds for one frame. And further, there are more optimization for security, which leads to enabling additional power saving on the sensor. But Rick will come back to that on the security variant and the tag mode, how they work together. Yeah.
Perfect. Thanks, Ariel. Question for you, Haran. What are the benefits of alleviating dual voltage signaling supported by LRTE?
Oh, right. So within the LRTE feature, there's a provision to alleviate the need for high voltage signaling for low speed control and low voltage signaling for the high speed differential transport comprising the pixel data. By alleviating the need for the high voltage signaling used for control, one of the first benefits is that when you're using newer process nodes, the current leakage impediments that often comes with transistor stacking is removed. And then second, as you know, Peter and Ariel has alluded to, we are very much in the process of facilitating longer reach for spanning beyond mobile applications. So when we think about spanning a longer reach and look at this from a physics perspective, and if we are using dual voltage signaling, a receiver's ability to discern the high voltage, low speed control and the low voltage, high speed pixel transport, it diminishes if the delta drops below around 70, 75 puffs. So with the typical transport of where we have around, say, 3 puffs, there is a physics constraint that we are also trying to break free of, which falls around like 25 inches, maybe 20 inches. So those are a couple of key, very important imaging systems reasons driving for the removal of a dual voltage signaling.
Great. Thanks, Haran. Maybe one more question to you, Ariel. Is it mandatory to use SEP with APHI?
No. Well, yes and no. So when you are running over APHI, the adaptation layer for the CSI-2 protocol, the PAL CSI-2, mandates to use SEP. Now, when you are making the functional safety end-to-end and you're implementing CSE, this is completely agnostic to the APHI, yeah, or to any other PHI. Then you can select to choose either SEP protocol or FSET protocol for the end-to-end protection. On the APHI, you use SEP to make the, I will say, the so-called bridge-to-bridge protocol from PAL to PAL, from protocol adaptation layer to protocol adaptation layer. So, but at the end-to-end, you can select one or the other.
There are many ways to learn more. Ask questions of MIPI. Your questions, if you do reach out to admin@mipi.org, they get routed to subject matter experts around the organization. As I mentioned earlier, there's an introductory guide to MIPI Automotive Security Solutions, MAS. We have a blog, no shortage of information from MIPI. And also you can join the MIPI Automotive mailing list. We do keep everybody up to date. There's not a lot of traffic on that, so feel free to add yourself and subscribe to that list. You'll get updated as automotive news comes out of MIPI Alliance. And again, if you do need to reach out to MIPI Alliance or any of the speakers, feel free to use that admin@mipi.org address. Thank you very much and have a good day.
Thank you.